Thanks for giving me this opportunity to present in this research seminar. As Jen pointed out, my name is Mubeen. I'm a postdoctoral researcher in Department of Chemistry and Department of Chemical Engineering at UCSB, and today I will be talking some of our recent efforts on gathering energy from sunlight and converting them to useful fuels and chemicals. And before I start my talk, I'd like to thank these wonderful colleagues without whom this work wouldn't have been possible, and also my PIs, Eric from Chemical Engineering Department, and Martin and Galen from Chemistry Department. So before, I don't want to preach the choir here, but we all know that we need to develop scalable, cost-effective, carbon neutral energy sources. So the overall goal in this research theme is to establish an interdisciplinary effort to advance fundamental science and engineering to come up with ways, cost-effective ways to produce fuels just as plants do. So it's basically mimicking natural photosynthesis. So that's the overall goal, and there are many focus areas that we specifically look into. And one of the areas is low-cost synthesis of these artificial photosynthetic systems. We see what the ways to create artificial photosynthetic systems in an inexpensive way and ways to stabilize them. That's one major area of focus. We are also working on identifying novel materials, something like plasmonic metals, as sources of photoexcited carriers, and trying to see if plasmonic metals can be used either by itself alone or in conjunction with the traditional semiconductor materials for artificial photosynthesis. And we are also trying to have combinatorial synthesis and rapid screening so that you could have evaluate wide parameter spaces so that you could test and screen a large efficacy of materials. And recently we are also trying to come up with in situ electrochemical and optical probes so that you could get a mechanistic understanding of this complex photosynthetic systems. But for this talk, I'll be mainly focusing on low-cost synthesis of artificial photosynthetic systems. Okay. And before I go into in detail why we need fuels and chemicals as storage options, why we wanted to use renewable energy sources and generate fuels and chemicals as storage options. So this is a single chart that gives us volumetric energy densities and gravimetric energy densities of different storage options. The most commonly used is you could convert sunlight into electricity, and you could store them in batteries, or you could convert them into liquid fuels. And as you could see from the numbers, the liquid fuels do have much higher energy densities, almost 100 times more than what the batteries are. This doesn't mean that the battery research isn't important. Battery research is absolutely important, but if you are thinking of a large-scale solar energy deployment, then probably storing them as fuels and chemicals might be a better alternative. So that's the overall theme. We wanted to use chemical bonds to store this energy, and these are a couple of well-studied incarnations, if you may call, to use sunlight and store them as chemical energies. For example, if you see water, it's thermodynamically uphill to split water to produce hydrogen and oxygen. So water is clearly a very, very stable substance. So the idea is use sunlight, split water, produce hydrogen and oxygen, and compass them back and get the energy back out. And you could either use water to split, or you could also reduce CO2 to produce fuels, and so on and so forth. So that's the basic theme. And there are many ways to synthesize solar fuels, and we are very interested only in solar fuels using photoelectrochemistry. So this is a very well established system. It's a mature system. It's currently available. You could use PV panels, produce necessary photovoltages, connect them to an electrolyzer, have the necessary catalyst, and you produce hydrogen and oxygen, and put them in a fuel cell, generate electricity, and back and forth. So the advantages, it's mature technology. You could currently use them, Audi uses it, but the cons is it's still currently very expensive. So it's a good area of research to come up with cheaper catalysts so that you could make the electrolyzer a little inexpensive. The other way is can we combine all these systems, the solar cells, the electrolyzers, and everything in one integrated architecture? And as you could see, the advantage would be definitely will be an inexpensive system, but the disadvantage is it's still not an unproven technology. So that's what we are focusing on this particular research to come up with an integrated architecture to convert solar energy to fuels and chemicals. And this is just a single slide that gives a primer on photoelectrochemistry. Most of the people in this room know how it works. You have a light absorber. When a photon is incident on it with an h mu greater than the band gap, you create carriers, and by appropriate interfacial engineering, you could extract these carriers and give them to the necessary catalytic sites to do the necessary reaction. Okay, so there are only three main steps: light absorption, charge transport, and catalysis. And if you are planning to do water splitting, you would have something, a good catalyst like platinum, which reduces proton to hydrogen, and here you might have something like ruthenium-based oxides that oxidizes water to oxygen. And if you have such system, you could envision something like a dispersed photocatalytic systems that it floats like duckweed in a pond. You just shine light on it and you produce hydrogen and oxygen, or produce any necessary fuel that you wanted. So that's the overall goal. And what's the materials consideration for it? So depending upon what product you are focused on, for example, if you are focused on splitting water to produce hydrogen and oxygen, this is the photovoltages that you need, around 1.23. If you are interested in reducing CO2 to necessary fuels and chemicals, and the counter reaction is water oxidation, these are the photovoltages. And if you are interested in halogen production, something like bromine, you have lesser photovoltages. So basically, depending upon what your final product is, your photovoltages depends on that. So you have to create a photosynthetic unit that has the necessary photovoltages to do this chemistry, and we are only focusing on chemistries or systems that can do this without any additional energy input. So only sunlight as your sole energy input, no other electrical applied bias or so on and so forth. So that's the starting point. So come up with a photosynthetic system that matches these photovoltages. And of course, we don't take here, these values do not take into over potential losses. These are thermodynamic values. Of course, there are kinetic limitations that pushes, that adds a little additional photovoltages. So that's something to be taken into consideration. So once you have the necessary say photovoltages, you also need necessary current so that you could carry these reactions in a very efficient way. And this is just a graph of solar photon flux plotted as a function of energy, and if you integrate it, you get the maximum photocurrents that are achievable. And we are mainly focused on getting at least 10 milliamps per centimeter square, so that your efficiencies is at least, solar to fuel efficiency is at least 10%. And that's the target from DOE, and so we are mainly focused on getting at least 10 milliamps per centimeter square, and that will depend upon what band gaps that you choose. So we know the voltages, we know what the band gap of the materials is, and we know the target efficiencies. So that's the materials consideration. And say if we have these materials, is it possible to do it? For example, this is a PN gallium arsenide solar cells. It has a photovoltage of around 2.5 volts. And the video doesn't work. So, but the overall objective is, let me just show you. So this is our overall objective. So if you have the necessary solar cells, and if you are able to stabilize them, and say if this is a particular solar cell that's illuminated, that's immersed in an electrolyte. The electrolyte is an hydrobromic acid. So once it splits, it produces hydrogen and bromine, and you shine light on it, you produce hydrogen, it escapes to the top, and probably you could collect the hydrogen and you could do whatever you wanted to do. If you're interested in converting them to electricity, you could run them through the fuel cell with an hydrogen oxygen fuel cell and generate electricity. And the bromine is a liquid that's collected at the bottom, and it's a very valuable fluid, valuable chemical as well. So this is the overall idea. So it works. But the challenge is these systems, these efficient systems, or unstable, although we get 13% solar to hydrogen conversion, and the DOE target is we are already over 10% efficiencies, but the problem is this efficiency continuously drops with respect to time. So they're pretty unstable, and currently the ways to make them are very, very expensive. So this solar cell costed around like $10,000 per meter squared. So it's very, very expensive scenario to use these kinds of materials to create your fuel. There are stable systems, but unfortunately these stable systems are mainly wide band gap oxide, so they are inefficient because they absorb solar. Their absorption is very limited. So the question that we'd like to ask in this research effort is like, can we stabilize these high photon conversion efficiency materials so you could carry out this chemistry for many, many years? And if so, can you synthesize them using low cost manufacturing tools? And for the reactor, we came up with a nanoparticle bed system rather than a photocell, a planar system. The reason is based on this particular study done by James and Baum. It's a wonderful techno-economic analysis submitted to DOE. They came up with 4 reactor designs and found this particular design to be very inexpensive. So the way this reactor works is you will have a colloidal suspension of your photovoltaic cells immersed in the electrolyte, freely floating. You produce, you shine sunlight and produce the necessary fuels and chemicals. Of course, you have to come up with the ways to make colloidal suspension of PV particles with the necessary voltages and the necessary currents. And not only that, you have to protect them because most of the high efficiency semiconductors do photocorrode. They like to oxidize themselves rather than oxidizing your solution. So you have to protect them so that only the necessary catalysts are exposed to the solution. So this is the reactor design that we are aiming for, and if you are able to do this, then the cost of hydrogen production based on their calculation is $63 per kilogram, and one way to look at this number is 1 kilogram of hydrogen energy equivalent is 1 gallon of gasoline. Of course, this study does not take into the account the storage of hydrogen and so on and so forth, but nevertheless it gives us a number to work with. And it assumes, there is a big assumption that this system is very stable, that's greater than 10 years of stability, and you have to do the solar to hydrogen at 10% efficiency. So the take-home message is, yes, cost competitive fuel production is possible, if it's a very big if we can develop and demonstrate high capture area stable nanoparticles with the necessary photovoltages and which carries out the chemistry with necessary efficiencies. So that's the big goal. And this is our particle design. So we wanted to make these multi-component photosynthetic units. We will have a light absorber, just like how the solar cell works. We could either configure as a PN or a metal semiconductor Schottky junction with the necessary photovoltage, capped with the necessary electrocatalyst. So once you shine light, you create the necessary carriers. They are given to the necessary catalytic sites and performs the chemistry very efficiently. Now the question is, can you identify ways to create this particular particle design in a low cost way, and can you also find ways to stabilize them so that you need to have some protective coating so that the semiconductor does not see the solution at all. All the solution sees is your electrocatalyst, and these are the 2 specific objectives. And the way we do it is using this wonderful technique called host-guest templated synthesis. It's pioneered by our collaborators Galen and Martin, who have shown that if you use an inorganic template, something like mesoporous silica or a porous alumina, you start with this host template, you infiltrate them with the necessary materials, and voila, you have your final structure. And we have shown that we could use either silica or alumina to grow these structures, and we have done them using simple methods like calcination or chemical or electrochemical means. We could do metals, metal oxides, semiconductors, and so on and so forth. And the nicer thing is these templates not only act as your growth template, but also protects these materials, because the silica and alumina are pretty stable in the pH ranges that we wanted to carry out, and they are transparent. And we believe that this process it's already been demonstrated. For example, making mesoporous silica and porous alumina have been shown for roll-to-roll processing, and the ways we infiltrate these pores is electrodeposition, so it's a well-established process. And this is just a very one simple thought experiment that we did to show that this is possible. So this is a porous alumina. We infiltrated with individual photovoltaic panels, if you may call so. So here your light absorber is cadmium selenide. We form a Schottky barrier over here using a polymer called P dot, and we cap the cadmium selenide with a catalyst platinum for hydrogen evolution. And the nicer thing is, if you could see, each individual panels are isolated from each other electronically. So even if certain panels fails, you still carry out the chemistry, and we could make these 10 power 10 such structures in per centimeter squared. So even if you have thousands of these structures fail, you have millions of these cells still carrying out your redox chemistries. And we were able to show, this is again a video, I will just skip it. We showed that like we were able to make these kind of particle bed systems. We did show that the semiconductors that were infiltrated in these pores are pretty stable, as you could see from the amount of hydrogen evolved with respect to time. These semiconductors do fail in seconds if they are not protected. So this gives an idea as it does work. So the take-home message is we can create nanoparticle bed systems as envisioned by DOE, and we did achieve stable operation. And definitely the future challenge is to improve the open circuit voltages, because these cells do have an open circuit voltage of around 0.5, not enough to do the necessary chemistries that you want to do. And with that, I will just leave the summary for you to read, and thanks to you, and thanks for this opportunity.